Hello everyone, my name is Salve Martelli Carpi and my project is the impact and deformation analysis of a car's front impact bar. So modern automobiles are often compared, usually by older people, to older vehicles from the 50s, 60s, and 70s. And one of the main points of comparison are those big, heavy, and strong metal bumpers that those cars used to have. They always still people those people usually say that those older cars were more protective on impact because they were tougher and harder. Uh, they always complain that modern bumpers are made out of layers of plastic and other materials that are thinner. But however, what they don't know is those modern bumpers they are made out of those layers, many different structures and materials to help absorb and then dissipate the force of an impact. However, the innermost layer of protection is can be seen as a reminiscent of those old metal bumpers. However, it is also made to assist with the energy dissipation. So here you can see several examples of an impact bar in different kinds of vehicles. As you can see on the left picture, it is one that probably had a severe collision on maybe a light post, I would assume, based on the type of deformation. And on the right, you can see one's in a normal situation. So car manufacturers clearly have performed tests and analysis on those materials and the design of those impact bars. However, wasn't able to find much information online, either from the manufacturers themselves or any research paper. So this project can be seen and it can be a good avenue to better understand the importance of this component since not much information is available. Main objective is to understand and analyze how a car's front impact bar deforms in a way to absorb the energy of a frontal collision, which better protects the passengers of the vehicle, and also visualize the different behaviors of the different materials commonly used in this application. So here you can see the geometry that, that I created for this project. So it was based out of an impact bar from a Chevy Impala, I believe, from 2016 to 2018. They used this model. Um, However, for whenever I had to put that geometry on Nancy's workbench to analyze, it was too complex, so I had to simplify it, as you can see on this mesh picture. So the mesh size that I used was 15 millimeters. And as you can see there, that rectangular block was the object that I used to simulate a full frontal collision on the impact bar. And I did that by using an explicit dynamics analysis on Workbench. And I used two different materials for this. One was a standard aluminum alloy provided by ANSYS, and also the structural steel. Main reason why I picked those materials was because I wasn't not able to find any information beyond the fact that some of those bars are made of aluminum and some of them are made of structural steel. As you can see, based on that specific model that I created, the mass of those bars was around 31 kilograms for the aluminum and around almost 89 kilograms for the structural steel. There's a big weight difference. It's almost more than double, almost triple the amount. And for the test, I used a velocity of 50 meters per second, 100 meters per second, 150 meters per second, with a simulation time of 0.005 seconds. The main reason for this simulation time was that anything above that, the simulation was taking way too long. And sometimes the results would fail, it would deform too much, and even for lower velocities. So the main reason why I chose these three velocities, as you can see, I made an estimated force of impact for them for using the weight, the mass of those bars for the two different materials, and then I estimated the equivalent velocity for 1,600 kilograms vehicle, which is at somewhat of a standard weight for modern vehicles. And as you can see on an impact, the equivalent velocity for this type of impact on all the situations was relatively slow. If you think about it, the highest one was about 8.3 meters per second, and my goal originally was to use 100 meters per second impact, which is 100 kilometers per hour, which is around 28 meters per second. But doing the conversion, and because the mass of the bars is way smaller than a full car, the results were not. It was barely deforming the bar because of the lack of weight, even at 100 kilometers per hour or 28 meters per second. So what I did was just increase the velocity so that I would get actual substantial deformation on the bars, and I was able to achieve that, especially with the 150, as you will see on the next slide, which is a deformation analysis. So as you can see, on the first two pictures for both aluminum and structural steel, there was already a plastic deformation, but they were not really significant. But as you can see on the next four pictures, especially on the later ones, there was a very big deformation. One thing that is important to know is that those deformations are larger than they would be in real life, mainly because all like for this scenario, all the impact is being aimed and at the bar itself, so you won't have the bumper or anything in front of the bar or all the rest of the car behind it, so that will also help absorb that impact. So this is an exaggerated deformation for these bars. So as you can see here, I have a summary of the results. Deformation for the steel was surprisingly to me, it was significantly larger than the deformation that could be seen on the aluminum bar. As you can see on the 150 meters per second, it was, I wouldn't say almost double, but it was significantly um, larger on the, actually, for the 50 meters per second, it was significantly larger. I'm sorry, I messed that up. Um, but this was something I was surprised after the analysis. I redid it a couple of times to make sure that those results were correct. And here for the stress analysis, you can see that uh, you can see again the same deformations, but you can see how the values change for the different velocities of the impact. And as you can see, um, mainly on the later images, on the images on the middle and right, most of the bars were already failing. And here you can see the maximum stress values for all of them. So in all three situations, the maximum stress was larger than the yield strain of the material, which is 250 for the steel and 280, I believe, for the aluminum. The interesting thing is that, I'm not sure if you're able to see here, but the maximum stress on all situations were usually located on these corners right here instead of on the rest of the of the model, which was something I thought it was quite interesting. And it was usually lower wherever the contact area between the bar and the block, which basically didn't deform, it just almost stayed flat, and the other areas were the ones that deformed more and had more stress on them. So now I'm going to talk a little bit about the material specifications. As I said earlier, I wasn't able to find a lot of information regarding the specific materials that are used on these impact bars, besides the fact that they are either made of steel or aluminum. So because of that, I just decided to use the standard aluminum alloy and structural steel alloy for the simulation, which could also be, which most definitely impacted a little bit on the deformation and on the stress analysis. since we don't have the specific details, specifications of these materials. As you can see here, the density is what I use to get the weight for my model, the mass value for the model that I also use to estimate the force of the impact, as well as what the velocity would be for a full car to generate that kind of impact. So concluding this project, first of all, it was a very interesting process to actually learn how to properly use ANSYS. It was something that have never used before. So it was a great learning experience to be able to apply this to like some real world situation, and also be learning as I went through the project. So concluding, you can say that even at relatively low speeds, these frontal collisions can generate a lot of force. As you can see, those are metal bars, have relatively heavy metal bars that were significantly deformed, even at, as you could see on the speeds, relatively low speeds, as if they were in a vehicle. Again, you would have more mass and more struggle in all other structures in the front and behind those bars, but still the deformation that you will be able to see even on those later impacts was very, very big. Which also ties up to the fact that shows how much vehicular safety has improved. If you show anyone this kind of deformation on a bar and say that a person was involved with that, they will most likely say that they ended up in a bad situation. But as you can see with the estimated speeds from those impacts, pretty much no one would be significantly harmed from one of those, or any one of those collisions, frontal collisions. It makes an interesting point of comparing both materials and how they performed. So aluminum had a significantly less deformation than steel. However, it is seen also significantly more expensive to produce than steel, but on the other hand, it's significantly lighter. So depending on the application, if you want to have maybe a car that is more focused on fuel efficiency or performance, you definitely want to go with aluminum, mainly because of the weight, since their performances are not really, even though they're different, they're not that different that it would make sense to have a part that is almost 3 times more heavier than an aluminum one. But again, they still, it's way heavier, it has more deformation. We could aid to a better impact absorption. However, depending on the type of application, it might make more sense, mainly because of the price advantage, which I wasn't able to get a specific number, but from what I saw, it's usually between 20 to 30% cheaper to make a steel part than aluminum. One thing though that probably would impact the overall weight is that, from what I've seen, they steel models for those impact bars, they are usually stem steel, so they are simpler shapes than what I used, and usually thinner, so that weight difference wouldn't be as significant. Again, it was a great experience working on this project. I learned a lot, mainly on how to use ANSYS and Workbench, and analyzing different models and properties, and thank you very much. I hope I was able to provide a good insight on these impact bars and their deformation. Thank you very much.